Viewers, this is Math Without Tears. This problem was sent to me by a student. This is a differential equation, the first order linear differential equation. If we look at this differential equation carefully, we see that this is a variable separable differential equation. Now, the problem here reduces to separating the variables and resolving the problem. How do we separate variables? We could put the x variables on one side of the equal sign, the y variables on one side of the equal sign. How can we easily do that? There are so many ways we can approach this problem. One way is to get rid of tan y, which is on the first term. And how can we do that? We can divide each term by the tangent of y. We divide here by the tangent of y and here by the tangent of y. Once we do that, tangent will cancel here and we will have 3x4 of x times the differential of x plus 1 minus the x4 of x times sec squared y divided by the tangent of y dy equals 0. Now, we can see that the first term here depends only on x, but the second term depends on x and y. Now, it is easy for me to get rid of 1 minus x4 of x. And how can we do that? We can do that by multiplying each term by 1 minus x4 of x to the power of -1, or we can go ahead and divide each term again by 1 minus x4 of x. Now let's do that. If we divide here by 1 minus x4 of x, we still have the x plus we divide here by 1 minus x4 of x times sec squared y divided by tan y times dy equals 0. In this case, this is 0 divided by 1 minus x4 of x. In this case, we realize that the left hand side becomes 3x4 of x divided by 1 minus x4 of x dx plus this 1 minus x4 of x cancels out and we have sec squared y divided by tan y. Let me write that down. Sec squared y divided by tan y dy equals 0. Of course, we can subtract this term on both sides, or we subtract this term on both sides. Now, I would like us to subtract this term on both sides. 3x4 of x divided by 1 minus x4 of x dx. Let's subtract that on both sides. We will have sec squared y divided by tan y dy equal to, when I subtract on both sides, I'll have 3x4 of x divided by x4 of x minus 1 times dx. You might now be wondering, where is the negative? The negative was, we were supposed to have a negative here. The denominator here absorbs the negative and becomes x4 of x minus 1. So, at this point, we can simplify the left-hand side before we continue applying integration sign on both sides. Now, in order to do that, I need to understand what sec squared y is in terms of tan y. Remember, in trigonometry, where you have this very familiar identity, cos squared y plus sine squared y equal to 1, I can go ahead and create sec squared y. If I divide each term by cos squared y, and here cos squared y. This will cancel. I'll have 1 plus sine squared y divided by cos squared y should give me tan squared y. And 1 over cos squared y is what? It is sec squared y. Now, it means instead of sec squared y, I can write 1 plus tan squared y. Meaning I can write 1 plus tan squared y divided by tan y. So that everything becomes tan squared y over tan y. No sec squared anymore. 3 expo of x divided by expo of x minus 1 dx. Remember this rule. If we have a plus b divided by c, we can always write it in this form. A over c plus b over c. C is a common denominator for these two terms. So we can apply that here, and we have 1 divided by tan y plus tan squared y divided by tan y. All of these dy equal to 3 expo x minus 1 dx. I can apply integral sign on both sides. If I apply the integral sign on this side, the integral sign on this side, remember that this is an indefinite integral because we have no limits. And when we have no limits, we must add an arbitrary constant k. So we have an arbitrary constant this way, which is k1, an arbitrary constant on this side, which is k2. If I put both of them together, I will have a constant k. This implies I can integrate these terms separately, integral, and I can also change this. 1 over tan x is sine, tan y is sine y over cos y. This is the same as cos y divided by sine y. So instead of writing 1 over tan y, I can say cos y divided by sine y dy plus the integral of, I have tan squared y divided by tan y. This is going to cancel. The square cancels, and I'll have tan y dy equal to. I can factor out the 3 because it has nothing to contribute in the integrand. And I'll have expo of x divided by expo of x minus 1 dx plus k. Now let's clean this side. Now I will transform this side. I will transform the integral of cos y divided by sine y dy this way. And before I transform that, let's recall a rule that we use in integration. Each time you have the integral of 1 divided by a particular function times the derivative or the differential of that function, the answer is ln the absolute value of that function plus a constant. Now, my integration here becomes easier if I apply this rule. So the first term here becomes integral of 1 over sine y. Normally, we are supposed to have cos y divided by sine y. But I can put these, the differential of y can absorb this one, cos y, to become the differential of sine y. Remember that if I go ahead and find the differential of or derive sine y, I will have cos y. So I want to make these look like this rule right here. So I can integrate easily without letting u to be equal to sine y and then looking for du by dy and all of that. Now, that's the first term. The second term is integral of tan y. Integral of tan y is same as integral of sine y over cos y. So I can say 1 over cos y times the derivative of what can I differentiate to have sine? I can differentiate cos to have sine. But then when I differentiate cos, I have the differential of cos x gives me negative sine x. Meaning if I put a negative sign here and I put my cos here, when I derive cos y, I'll have negative sine y, which will cancel the negative sign. And the right hand side becomes 3. I also want to transform this so that it has the same form with our general rule. So I can say this is 1 divided by x power x minus 1 times the differential of x power x minus 1 plus k. I was supposed to write x power x divided by x power x minus 1, but I chose to write 1 over x power x minus 1 times the differential of x power x minus 1. Why? Because if I differentiate x power x, I will have x power x. If I differentiate negative 1, I'll have 0. So I haven't changed anything. Now, applying this rule, the integral of 1 divided by a function times the differential of that function gives me ln the absolute value of that function. So this becomes ln the absolute value of sine y. Now, we have a negative sign. I can take that negative sign out. And we have 1 divided by cos y times the differential of cos y. That gives us ln the absolute value of cos y. Equal to 3, we have 1 over x power of x minus 1 times the differential of x power of x minus 1 gives us ln the absolute value of x power x minus 1 plus our constant k. At this point, we can call this the general solution of this differential equation. We can continue and put this in other ways, but if you end here, you have had the general solution. But let's continue putting it together. We can apply the laws of natural log, or the laws of logarithm that says the logarithm of a minus the logarithm of b equal to the logarithm of a divided by b. All right. So the natural log of sine y minus the natural log of sine of cos y can be written as the natural log of sine y divided by cos y, according to that rule. So equal to, now, n times the log of a is the same as the log of a to the power n. So 3 times the natural log of x power of x minus 1 should give me the natural log of x power of x minus 1 raised to the power 3 plus k. Of course, sine y divided by cos y is what? Tan y. So I can go ahead and put ln the absolute value of tan y equal to ln x power x minus 1 plus k. How can I get rid of the natural logs on both sides, or the natural log on this side to have tan y by itself? I can find the exponential of both sides That means tan y is equal to the expo of ln of expo of x minus 1 to the power 3 plus k. This means tan y equal to expo ln of expo of x minus 1 to the power 3 times expo of k. From indices, we know a to the power m plus n equal a to the power m times a to the power n. From the laws of indices, we have that this is my m and this is n, and we can put it in that form. So this implies tan y equal to the exponential of the ln of any function is that function. So this becomes expo of x minus 1 all to the power 3 times expo of k. Again, expo of k is just another constant c. So this means y equal c expo of x minus 1 all to the power 3. Now, for any given value of c, we can have a particular solution of this differential equation. But at this point, this is the general solution of the differential equation. Peace.